Okay. So, in today's lecture, let us consider convergence at a point of discontinuity, right. We proved in the last class that there is convergence at points where it is continuous, and we arrived at conditions linking the Dirichlet kernel and the function g, right, that satisfies at the points of continuity, right. I mean, we have that precise equation, I can just pinpoint to you. So, if you set this g of 0 to 2 times f dash of x, right, then we can extend this function g of u across u equals 0 as a continuous function, and this is a very important step to show that there is convergence. Now, let us look at convergence at a point of discontinuity. So, the first and the foremost thing that comes into your mind is not all functions are continuous and periodic, and the other part is, if we consider periodic extensions, it may not necessarily result in a continuous function. There are plenty of such cases, right. What we did, f of x equals x, was one such case. We start with the following definition. We know from basic calculus, limit f of x minus h tending to 0 plus is f of x minus 0. This is the left limit. Similarly, we have limit h tending to 0 plus f of x plus h is f of x plus 0. This is the right limit. When the function is continuous, the left and the right limits must be the same, and it has to evaluate to the function at that particular point, right. But it may not be the case, but we will see the importance of these left and right limits. Similarly, we can recall the differentiability conditions. A function f is left differentiable at x if f dash of x minus 0 is limit h tending to 0 minus f of x plus h minus f of x divided by h. This is the left differentiable condition. Similarly, a function f is right differentiable at x if f dash of x plus 0 is given by the limit h going to 0 plus f of x plus h minus f of x divided by h. So, you can think about, if you are going like this, imagine you are computing the tangent and you are going like this, then this is basically derivative of x minus 0. On the other hand, you have this function like this and you are approaching like this. This is x plus 0, right. So, this is a sort of a pictorial notion that you have to get when you actually evaluate these limits. Now, for f of x equals minus x over minus pi less than or equal to x less than pi and periodic extensions, f of pi plus 0, f of pi plus 0 is minus pi, f of pi minus 0 is pi. You take f dash of pi minus 0 is 1, f dash of pi plus 0, this is 1. Now, if you consider f of x is x for 0 less than or equal to x less than or equal to pi by 2 and pi minus x between pi upon 2, between x lying between pi upon 2 and pi, f dash of x is not differentiable at pi upon 2. You can see the slope, how things are changing when you are approaching just around pi by 2, right, whether you are just going to the left side or on the right side. You take the derivative, compute the left and the right derivatives, you will conclude that it is not, the limits do not agree. Now, once we get this kind of feel, I mean, you have a function, it is not necessarily continuous, but we take an extension of the function and there are continuities because of the periodic extension. What can we say about the convergence at such a point or at such points of discontinuities? Okay. So, this leads us into a theorem. The statement of the theorem is as follows. Suppose f of x is periodic and piecewise continuous. Suppose x is a point where f is left and right differentiable but not continuous. So, look at this subtle point. There is a left derivative, there is right derivative, but it is not continuous. the Fourier series of f at x converges to f of x plus 0 plus f of x minus 0 upon 2. It is basically the mean of the function on either side, mean of the function evaluated at the left and the right values. Okay. So, let us see the proof of this theorem. Let us slightly deviate from step 4 of our previous theorem. So, if you recall step 4, I think we said the kernel integrates to 1, right, from minus pi to pi, that is the result. So, we will slightly deviate from that point. So, integrals, it is a symmetric kernel. So, integral 0 to pi p n of u du is integral minus pi to 0 p n of u du, and this is 1 upon 2. Let us call this equation 1, right, just for your recall. P n of u is 1 upon 2 pi sin n plus half u, put this brace here, upon sin u divided by 2, right. That is why we are getting this result. It is an even function, therefore hence this equation. Now, what do we need? What do we need? To prove the theorem, we need to show integral minus pi to plus pi f of u plus x times p n of u du heads as n goes to infinity to this equation, which is f of x plus 0 plus f of x minus 0 upon 2. Now, we already have a hint here. So, break this limit from minus pi to plus pi as from minus pi to 0 and then 0 to pi, okay, and then it is easy for you to see through this. Now, integral 0 to pi f of u plus x p n of u du, this heads to f of x plus 0 upon 2 as n goes to infinity. Just taking one portion, right, and this is basically integral, this is basically half of the whole kernel, and therefore, this is just basically x plus 0. Now, this is done symmetrically for the limit from minus pi to 0 f of u plus x p n of u du as n goes to infinity heads to f of x minus 0 upon 2. right. Why you would do it exactly the same way, right? You just put this x plus 0 here, exactly the way we did, and show that that is basically heading to 0, right, using the same arguments that we did. Using the definition of Pn of u, 1 upon 2 pi integral 0 to pi f of x plus u minus f of x plus 0 upon sin u by 2. This is basically the g of u function form, sin of n plus 1 half u du. This heads to 0, and that is how we conclude that this is, if you take this function out, you have this equation here, which is, I call this A, I call this B. This is where you get A from. Now again 1 upon 2 pi integral 0 to pi this heads to 0. So therefore this theorem is established, right. So you could put the limit here basically from minus pi to plus pi, just same thing. It is symmetric, so you take the limit from minus pi to 0, and here you take the limit from 0 to pi. This establishes this result. Okay. Now one of the key questions that would be bogging your mind is, what is the measure on the set of all such discontinuities, right. So when we have finite or countably finite such discontinuities such that the measure on that set basically heads to 0. If this happens, we are okay with the convergence proof, right. This is very important result, and I will not be discussing a lot of the aspects regarding measures and these analysis ideas, because it is out of the scope of this course, but I strongly encourage you to listen through the MOOC courses on analysis in math, and you will see all these details coming up. Okay. So basically start from set theory, and that is the reason why you do not want to have uncountably infinite number of discontinuities. So every point you are looking into is discontinuous, or the measure on that set is basically not heading to 0, then you have trouble because it does not get to 0. These results you will not be able to establish. Okay. So this is an important but subtle detail.